Welcome to the third video in this series, dedicated to the fundamentals of sound design. You can find the playlist with all episodes linked below, and every new lesson will be added there. So it becomes a real academic-style course you can follow step by step. In the very first video, we talked about MIDI and the history of synthesizers. So if you've arrived at this lesson without watching the intro, I highly recommend going back and checking it out first. In Lesson 1, I also suggested a free digital synth that you can download and use throughout this series. I'll be using it for all the demonstrations so you can follow along and recreate the patches and examples hands-on. This is Lesson 2, and today we'll dive into the technical foundations that we need in order to build up a proper understanding of sound synthesis. Let's get started. In this video, we'll explore some essential concepts that apply to all musical instruments, but are especially important when working with analog synthesizers. In analog synths, changing the voltage directly alters characteristics of the sound like pitch, intensity, and timbre. Let's start by distinguishing between subjective perception and objective parameters of sound. When we talk about pitch, intensity, and timbre, we're describing how we perceive sound. These are subjective, but each one corresponds to an objective, measurable aspect. Pitch corresponds to frequency, in hertz. Intensity relates to amplitude, in decibels. Timbre is tied to the harmonic spectrum, that is, the combination of frequencies that make up a waveform. In the world of synthesizers, these objective parameters are represented by waveforms, like sine, square, and sawtooth, and how they're shaped or modulated over time. Let's break down the core elements of sound and synthesis. Frequency. Frequency is the number of cycles a sound wave completes per second, measured in hertz. The human ear typically hears sounds between 20 and 20,000 hertz. Higher frequency equals higher pitch. Pitch. Pitch is how we interpret frequency in a musical context. On the staff, the higher the note, the higher and sharper the sound. The lower it is, the deeper and darker it feels. Intensity. This refers to how strong or loud a sound is. In acoustic instruments, it's like how hard you pluck a string. In digital systems, it's measured by velocity, how fast a key is pressed in MIDI. Spectrum, waveform. The spectrum includes all the frequencies in a sound. The waveform is the visual representation of this spectrum. Together, the spectrum shapes whether we hear a sine wave, triangle wave, sawtooth, square wave, or something more complex. Timbre. Timbre is the color of a sound, the quality that lets us distinguish a violin from a trumpet, even if they play the same note. It can be warm, sharp, smooth, harsh, bright, dark, or round. Timbre depends on the oscillator, the waveform, and how it's modulated and filtered. Voltage and pitch in analog synth. In analog synthesizers, especially modular ones, sounds are controlled using voltage signals. These systems usually operate on a 15-volt range. To control pitch, many manufacturers adopted a standard known as 1 volt per octave. That means increasing the voltage by 1 volt raises the pitch by 1 octave. Each octave is divided into 12 equal parts, one for each semitone. Mathematically, this means each semitone equals about 0.083 volts. So, the higher the voltage sent to a VCO, voltage-controlled oscillator, the higher the pitch you'll hear. The rise of polyphony and memory in synths, 1970s. In the late 1970s, musicians and designers began to demand polyphony and memory in synthesizers. Until then, creating a sound or a patch required manually connecting 7 or 8 modules. Each patch could produce just one voice. To play a chord, you needed to triple the setup. This all changed thanks to Tom Oberheim, who in 1974 created the SEM, Synthesizer Expander Module, a complete analog module without a keyboard, made to be combined with other systems. Then, in 1975, he introduced the 4-voice, one of the first polyphonic synthesizers. It featured a revolutionary keyboard that could manage multiple voltages simultaneously, meaning you could finally play more than one note at a time. This new kind of keyboard was developed by EMU Systems. It used digital scanning and a microprocessor to detect multiple key presses. As for memory, at first, patches were saved manually via the master panel, with a limit of 16 patches. But in 1978, everything changed with the release of the Sequential Circuits Prophet 5, the first fully programmable polyphonic synth, allowing users to save and recall presets with a single button press. Finally, another big shift was technological. Early synths used vacuum tubes, which needed lots of power and generated heat. The introduction of transistors made synths more compact, cooler, and more efficient. Thanks for watching Lesson 2 of our Sound Design Fundamentals series. In the next lesson, we'll dive deeper into the technical side, exploring the main module categories in modular synthesis. We'll break down what each module does and how they work together to shape sound. Before moving on, make sure you've downloaded Voltage Modular, the free modular synth we're using throughout this course. You'll find all the download links in Lesson 1. Check the description or the pinned comment. Don't forget to like, subscribe, and hit the notification bell so you don't miss Lesson 3. See you in the next one.